Um, yeah, so it's about the Bristol demo, the crowdsourced video streaming demo, and the idea is to show running instance of this demo where we have video streams coming in from Bristol all the way up to BT, where we have another video server which is consuming the videos and then broadcasting the video to the internet, which we all can see later on. Uh, all in while we are using metro hole components, we are using compute instances, we are using an optical network and disaggregated metro optical networks with edge computing capabilities, and then we are using service orchestration with OSM and with multiple domain SDN controllers which are spinning up VNFs and then stitching the VNFs with network resources using different SDN controllers. And then we have the individual VNFs which have some functionality. We have a DPI VNF which from which we can inspect some traffic, get traffic analysis, and there's a firewall VNF if you want to block some VLAN. So we have basically 5 VLANs, each carrying a different video stream. For the just for this demo, we are broadcasting the same video over all the VLANs, but we will be seeing 5 instances of the same video on the other side in BT, where there is another video editing server. What this will do is it will collect all those videos in one and combine them in one big video stream, and then upload the video to the internet. And at the end, we can see on Twitch the broadcasted video. And if you want, we can use the firewall VNF to block few of the VLANs to show that we can stop some video traffic based on some criteria, but for now we will be doing it manually. So this is the overall diagram of the whole demo. There is at the bottom the etc NFV network service representation of the network service with the DPI VNF and the firewall VNF and 5 VLANs interconnecting the VNFs. On the top we have the control plane and the data plane, which I will explain individually later on. So the data plane consists of 2 NFVI POPs, one at Bristol, hosted at the University of Bristol HPN lab premises. The other one is at BT Industrial Park in Ipswich. So it's almost, Emilio, maybe you can comment, it's almost 600 kilometers, right, between the two? Okay, so yeah, so that's the distance between these two POPs. So on the bottom we have the NDFF infrastructure, which is a dark fiber infrastructure from Bristol to Cambridge, and from Cambridge to Industrial, it's another link. So at each POP we have an OpenStack server, which consists of a controller and compute server, which is the Vim, the virtual infrastructure manager at this instance. This hosts the DPI VNF, which receives the crowdsourced traffic, and then this connects to a Voyager muxponder, which is in turn controlled by an open config agent. This is connected to now the optical network starts, which is connected to a ROADM, which we set up in Bristol as a combination of WSS, and then which is controlled by an open ROADM agent, which was contributed by Tim, but we modified to our ROADM, and the open config agent was provided by Connect, which we modified to the Voyager muxponder. And then this is connected to the Bristol to Ipswich optical link, and on the other side it's a mirror structure. It's the nodes are identical, except for instead of ROADM we have a WSS because of the limitations of the equipment we had while transporting. Uh, and many and so this is the data plane, and there are basically services that Metro Hall is providing. The first service, that is the end-to-end Etsy based network service. This includes the VNFs and the connectivity between the VNFs, the thing on the top that we see here. And then this is broken down into individual components, which is the deployment of VNFs by VIMs, and then the end-to-end L2 network service, which is requested between the client ports of the Voyagers, which is an Ethernet layer 2 based network service. And then there is an end-to-end optical network service between the line ports of the Voyager, which encompasses the ROADMs as well. So these are the individual network services, which individual connectivities, which then are used to interconnect the VNFs. So this is the data plane setup. And then before moving on to the control plane, we have an inter-partner VPN, which is provided by University of Bristol. So each partner is connected to this VPN, and each one can access the other one's local network. This is how we all are interconnected. The control plane components can talk to each other. Uh, while when I describe the control plane, I'll also describe the locations of all the control plane entities. So the control plane setup consists of net2plan, which is the planning software hosted in Cartagena, and then we have multiple components which are all hosted in HPN Lab. We have the orchestrator, the parent controller, which interconnects, which is responsible for the network connectivity between the VNFs, and then NetOS, which is the responsible for the packet connectivity between the Voyagers, the L2 network connection. ONOS is responsible for the optical connectivity between line ports of Voyagers. And then we have individual agents, OpenConfig agent, two OpenConfig agents for each Voyager, two OpenROADM agents. The OpenConfig agents both are hosted in Bristol. One of the OpenROADM agents is hosted in Bristol, and the other one is hosted in Kinet Pisa. The OpenStacks, each one is hosted respectively in University of Bristol as well as BT, and one of the Voyager is hosted in University of Bristol and the other one is hosted in BT. And the red connectivity here is the University of Bristol internal network, and the 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 components which are hosted elsewhere outside Bristol are interconnected to other components with the help of the interpartner VPN network. So this is, in the end, this is the network service that we are targeting, where we have crowdsourced video streams coming in through a couple of VNFs towards the video editing server. And it's actually, sorry, this should be two VNFs. And there are virtual links interconnecting VNFs which are translated to actual end-to-end connectivities by the Metro Hall control plane architecture. And then I'll go over a workflow. So at the start, the net2plan, it retrieves some information from OSM about the VNFs, probably how we. So once net2plan requests it's actually network service instantiation. Sorry, it requests the network services. So OSM starts with first deploying the VNFs. The VNFs take some time for activation at both VIMs. Once they are activated, then OSM proceeds to request the connectivity between the two VNFs. In this case, it's 5 VLANs, so I will first just explain the deployment of one VLAN between the VNFs. The other 4 will be similar, although there will be slight difference, which I'll let you know later on. So the OSM then contacts the parent controller via the IETF L2SM API, which is the WIM connector within OSM, to deploy the WAN connectivity between the two endpoints on one VLAN. And these endpoints are already registered at OSM, and OSM knows these endpoints because we are requesting a network service between two different locations. So OSM knows that to interconnect these two locations, the OSM needs to contact the parent controller, which will provision the connectivity between these two locations. The parent controller, which after some internal processing, it deploys the optical connectivity between the two sites. So we are fixing the wavelength here between the two endpoints because of the limitation of the dark fiber and some sorry, not the dark fiber, the Emilio, I think it's some ROADM in between, right? Some filtering going on. So once ONOS receives this connectivity request, it replies to parent controller that the intent is being compiled, and then in the meanwhile it compiles the intent. While the intent is being compiled, parent controller actually waits on the NetOS to discover the link between the Voyager switches, and it queries it continuously. So before the link exists, the ONOS is configuring the Voyagers as well as the ROADMs to create a light path between the two endpoints. And the parent controller is querying the NetOS packet controller to check if a link exists between the Voyager switches. Once the link has been discovered, it asks to provision a VLAN between the Voyager client ports. So earlier we had an optical net connectivity between the line ports of the Voyager. Now we need a client port to client port connectivity between the Voyager switches, and NetOS then configures the Voyager switches with the flows. It adds the VLANs to the respective ports and the internal bridges, and then the VLAN 311 is provisioned. And then the parent controller replies to OSM that the WAN connectivity is deployed, and this is how we have one VLAN which is deployed end to end between the two VNFs. For other four VLANs, the process is similar. However, this time the parent controller does not contact ONOS, as there is already an optical network connected between the two Voyager switches. So it just proceeds to provision the VLAN. So we have a result as well here. We for in the last week we ran 30 experiments, each one of deploying the same network slice, and we are still filtering the logs, so we do not have an average times for all the setup times, but we did set up one of the 30 readings here to show you sort of a gist of the experiment and how the setup times exist now and how do they correlate with the Metrohall KPIs. So initially we have the net to plan, information retrieval, NSD upload, and the NS instantiation time. And then we have the actual KPI, the slice setup time, which starts from here, because before this point is the planning phase. This is the actual deployment phase in which we are setting up the slice. Here the OSM first starts with the activation of the VNFs. At this point, once the VNFs are activated, we have the end-to-end connection KPI which starts. This is the connection, end-to-end connection is the time that is taken to deploy one VLAN between the two sites. At this point, the parent controller starts its configuration. It requests ONOS to deploy an optical network, and ONOS in turn asks Voyagers and ONOS in turn configures the Voyager switches and the ROADMs. Once the ONOS configuration finishes, that is the optical connection setup time. So it's almost 57.946 seconds, the bulk of which is due to the Voyager configuration. So it's almost a minute, which is the target KPI, which is a very good sign. This is because the Voyager needs some time to tune the lasers for the frequency. If Voyager is already configured for that frequency, this time is very less. I mean, very less. So once the optical connectivity is set up, the NetOS topology discovery starts between the two Voyagers, and the parent controller waits on this. So once the topology discovery finishes somewhere at this time, the actual VLAN L2 connection is deployed between the two client ports of the Voyagers. And then once this finishes, we have one end-to-end connection which is set up, and this is one VLAN deployed here. The other four times are the deployment of the other four VLANs for the whole network service. So we see here that the end-to-end connection is 132.8 seconds, which is a bit more than the KPI of the end-to-end connection, which is almost 120 seconds, 2 minutes. But this is because of the topology discovery mechanism of NetOS, which is a bit longer than we would hope for. But if this is shorter, then we can easily meet the KPI of the packet end-to-end connection. The slice setup time is almost 290 seconds, which is much less than the intended KPI of 1 hour. So this is well in limit. So this is the result that we gained, and we have 30 readings. We will average the setup times for all the. So there are multiple screens in this demo, so I will try to show as much as possible. Probably it will not be so easy to show everything together, but I'll go ahead. Probably I think it's Javier, you need to show your screen first. Go ahead.
Yes, and also we can see first in the console the total time of the load phase. Then we can see that the
That's
network
okay.
service is already uploaded, and the total time that the onboarding phase takes. Okay.
Okay, go ahead.
So
Go slow.
the next phase is to choose the network service descriptor from the available descriptor in the list.
Perfect.
Okay, we are already selected, and we have to choose the origin node. For example, from the
Yeah.
University of Bristol, and also the destination node in BT. Okay,
Okay.
then we have to set an emulated bandwidth to use it as an input in the algorithm. For example, 120 megabit per second, and similarly to the latency, the upper threshold to accomplish the latency, about
Mm-hmm.
100 milliseconds. Okay, this is more
Perfect.
than enough. And I think we have everything ready to click on the run button.
Mm-hmm.
Okay, so I'm going to click on the run button. We have to wait about 5 seconds, something like that. Okay, and everything, I think is everything went fine because
Mm-hmm.
we already have the OS instantiation code that everything is okay, and also the time that the algorithm takes to solve the solution and the total instantiation phase. It's about 4 seconds, something like that. Okay.
Okay.
And finally, we can see in the focus panel the route that the algorithm returns as a solution. Okay. Here
Mm-hmm.
we can see the total path from the University of Bristol, which is the first being already deployed, the first BNF, to the BT adapter pack, where the second BNF is already going to be deployed. Okay, and also we can see in the middle the total path followed by this path. Okay.
Okay. Okay. So right now the network service is being instantiated at OSM, and it's active at the OpenStack level. Now basically we need to go. We are basically having our own logging server here, which is receiving logs from most of the components. So the first message that Javier sent was NS instant. It was a message from OSM that it received a request to instantiate the network service. Then the VNFs were deployed, and then OSM sends a message of WAN connectivity deploying to the parent controller. And at parallel, we also have some logs from the parent controller. What parent controller has done is asked ONOS to deploy an optical connectivity between the two Voyager switches, and we have all these messages from OpenRODM and OpenConfig agents of the configuration of the components. So the RODMs are configured. We are waiting on the OpenConfig and the Voyager agents. So on here we also have some logs and screens for the Voyager as well. So this L4 is the transponder that we are looking for, and we would like to have both transmission and receive at this end. At this point, the frequency is configured to the 193.8 terahertz, and now the power is configured to the target power. And now we have both transmit and receive at both ends on Voyager 1 as well as I think this, yeah, on Voyager 2 as well. So at this time we are waiting on NetOS for the link discovery between the two Voyager instances, and here on the bottom I have a continuous query to NetOS, which tells me when the NetOS the link between the NetOS is up. So I hope so far everything is fine for everyone. I'll just show within OSM the network service that we have deployed. uh, I can show the graphical interface of that network service. It is quite garbled because you have 5 VLANs which are going into the VNF, then 5 VLANs going to the other VNF DPI, and then 5 VNFs going towards the video server. And then we also have a management network. If you can see here, management network 1, management network 2, which is connected to this VNFs. So if I want, I can easily go to each VNF. I can SSH to each VNF. Oops, sorry about that. I think probably because the VNF is getting up. Let me try the other one. Okay, I need to troubleshoot this. Yeah. In any case, if you see here, the link is visible in NetOS and it's up. So what the parent controller is doing is right now is trying to create a network service, an end-to-end VLAN using NetOS at the Voyager level. So we need to wait right now. So this is the VLAN 3011 between the two Voyager switches. So let's wait till the so in parallel we have the video server at University of Bristol, which is continuously pinging the other video server and at BT. So if we see here, we have 5 VLANs pinging at the same time. One of the VLAN ping is working, and one by one, the OSM will ask the parent controller to deploy the connectivity, and in the similar way, one by one, at the end, NetOS will deploy this connectivity. Now we have 2 VLANs. So let me go now to the display of the video server itself. So this is the video server at University of Bristol level, where I have 5 VLC media player instances which are broadcasting the video to 5 different VLANs. The video is same for demo purposes, so I will play here all the videos, and then we will see at the video server at the BT end. So this is the video server at BT end. As we can see, we have multiple VLAN streams, multiple video streams which are being received, and all are collected into one video. And at parallel, we are also streaming this video to Twitch. So let me go to Twitch. So this is running right now publicly. I can paste this link in the chat window as well. So as you can see, I have a video service that is being streamed all the way from Bristol to BT, and then it is being uploaded to the internet as well. So I will check once more whether I can log in to the VNFs, because I'm having some problem. I know I'm not spelling Zeta correctly. So right now I've logged into the firewall VNF. If I want, I can, for example, block one of the VLANs. So let's say if I want to block VLAN 3011, which I know in this firewall VNF I have a bunch of, sorry, I have a bunch of OVS switches which are connected to the 5 VLANs, and I can block the traffic on one of them. For example, let me drop the traffic on NetOS 6 switch. So I have 5 switches. So, and then I can show the flows that I have on this switch. So I have a drop flow. So if you see, 5 of the video streams are running right now, and one is blocked. In this way, I can play with the video streams. Let me delete this flow again. Sorry. And we'll see that this video will start again. So this takes some time to start because the video is being is buffered at the BT video server. So it takes some time from there to broadcast it to Twitch before we actually see the result. So this is the whole crowdsourced video demo. I'm broadcasting here the same video, but you can have multiple users broadcasting different videos of the same event, and you can edit and choose which video stream you want to use. DPI VNF. So we have the NTOP DPI VNF, which is running in the VNF, and we have all these interfaces on the VNF for per VLAN. So for example, ENS6, we can see the flows here. This includes the video traffic that I have shown you, as well as the ping. So I'm running pings in parallel, uh, so I can have a detailed view of the type of flows which are running through the VNFs. Unfortunately, this is not the premium version of NTOP. So in the premium version of NTOP, I can do multiple things. I can even block the traffic here. But for that purpose, we are already using a firewall VNF to block the traffic. So this is the purpose of the DPI.